Lecture AP 1.5 coming at you. We're talking about molarity, stoichiometry, the use of molarity as a gateway into stoichiometry, going from volume, okay, as most solutions are measured in, to moles using their molarity. Okay, we're also talking about something called metathesis reactions, which are nothing more than double replacement, non-redox reactions, sometimes called precipitation reactions. We're also going over a solubility rules, so to speak, and of course we're talking about net ion equations and combining those reactions and concepts into limiting reagent problems. So we're kind of building our tool bag, so to speak, the types of things we can do with stoichiometry, and now we're going to use exclusively molarity in milliliters of a solution. A lot of chemistry is done this way, so it's a very important type of stoichiometry. So let's get started, as we would say in New England. Okay, so any case, the first thing I'm going to do is start writing some chemical formulas, and I'm going to have to overcome these flies that are in the room here today. Any case, iron 2 nitrate, if you remember, iron 2 means it's iron plus 2. The reason for the stock system is because iron can be plus 2 or plus 3. The nitrate ion, and if you forget that, that's okay, you can look it up for now, is NO3 negative 1. You're going to learn all these common ions that are given to you. Now, the chemical formula, because iron is plus 2 and nitrate's negative 1, is going to be FeNO3. You need 2 of those polyatomic ions, those clusters of nonmetals, okay, to make the salt, and that's what this is, neutral. Okay, the next one is ammonium carbonate. Ammonium is that grouping of ammonia with holding on to a proton through a coordinate covalent bond. We'll talk more about that, but that cluster is plus 1 because you're adding a proton. And carbonate is a CO3 negative 2 ion, and to make this salt neutral, its empirical formula would have to be NH4. And you would have to need 2 of these for 1 carbonate. Over here, iron is still plus 2. If you notice, the charge is not changing. That's why it's not a redox reaction. We're not losing or gaining electrons. Okay, we're just kind of switching places. Carbonate is still CO3 negative 2, and of course this would have to be a 1-to-1 to make this electrically neutral. And ammonium nitrate, still got the same ammonium ions, okay, and nitrate ions. And we would put them together as NH4, NO3. Okay, let's evaluate their phases next. Okay, it's very important. These are going to be a solution reaction, but not everything's going to be a solution. For a double replacement reaction to work, or metathesis, we're going to have soluble compounds in the solution, which means these ions have to be free from their salt counterparts. Any case, the question is this a soluble compound? Well, how do I identify that without using and memorizing rules? Well, think with me. You have 4 atoms, and over a span of 4 atoms, you've got -1 charge being split across 4 atoms. That's going to make the charge density of -1 to be small, which means it can't attract this +2 very well, which means water can compete for those charges and pull that away. So this is going to be aqueous. Okay? Ammonia carbonate. Well, for the same reason, you're going to have 5 atoms, however some are small, stretched over a +1 charge. So you're stretching a +1 charge over a large area, and that's going to make the charge density to also be too small and not really attract carbonates very strongly. Therefore, water can come in, the negative part of water in this case can get in there and separate those charges and compete for those same charges. So this is also aqueous, and if you want to memorize, you can, but it would make sense that ammonium ions, because of their charge density, and nitrate ions are always insoluble compounds. Okay, and of course over here, let's go start over here. Ammonium, for the same reasons, and nitrate combined together are also going to be aqueous. All right. Now I call this a sham, NH4NO3, because, or last year I called it a Kardashian wedding, because NH4 and NO3 don't really stick together. We write it that way, but in truth what you have is ammonium ions in solution and NO3 ions in solution with water, of course, surrounding them. So we write it together, but that's not really true, and we're going to kind of fix that with this net ion equation. Iron carbonate, whoa, we got a +2 ion and a -2 ion, so we could probably make some generalities here that these charges are going to be strong enough to overcome the force of attraction for water, and they're going to prefer each other than water, since water, if you remember, has a partial negative side and a partial positive, pretty strong partial. It's almost -1 and +1, but still not enough to compete with these +2 and -2. So this is your precipitate, and that's your solid. Okay, now let's balance. I've got one iron, two nitrates. Notice I'm keeping the nitrates together. One nitrate, so I have to throw a 2 there. Two ammonium ions, one carbonate ion, one carbonate ion. We are balanced. And there's our chemical reaction. But this isn't a great way to write the reaction in chemistry. In chemistry, a lot of times you want something called a net ion. We want to get rid of something called spectators, the ions that really aren't doing anything. In iron nitrate, we really have iron atoms hanging around. And I'm going to change my ink here. We have iron +2. We have nitrates. They're not really together. They're together as a salt, as a solid, but once they hit the water, they separate pretty well. And you've got ammonium ions coming together. Separating as a solid into solution. Okay? And what happens is, clearly this iron +2, when it comes in contact eventually to this -2, comes together, and it makes a precipitate. So when these guys collide, okay, is how Day would say, you would make this precipitate. The other two ions never come together, and that's why writing them together is misleading. So what we like to do in chemistry is write something called a net ion reaction. What exactly reacted? Well, an iron +2, aqueous, it's not elemental iron, plus an ammonium ion, okay, an ammonium ion, a carbonate ion, all right, came together. I'm not going to sing again. I'll leave you alone. And you get the iron carbonate. And of course, solid. That is the bottom line. That's the net, getting rid of spectator ions that are, I just keep making mistakes. Get rid of the spectator ions, okay, that are not doing anything. So I'm getting rid of the nitrates and the ammoniums, okay, and I'm canceling them out too because they're not doing anything. All right, so I'm just left with what actually reacted. And of course, I'm not forgetting my phase, which I almost did. Okay, so there we go. Now we have our reactions. We understand what really is happening through the net ion, although you probably won't need the net ion for this type of problem, but it's good practice to know how to do that or what that's all about. So what are we going to do now? Okay, well now we're going to do our limiting reagent part of this problem, just like we've done before, except again we're going to use the molarity as a gateway. So I'm going to start my work with 125 milliliters, okay, of my iron nitrate. And what I'm doing here is, if you remember, I'm trying to figure out how much milliliters of the ammonium carbonate do I exactly need to make all of my iron nitrate. I'm trying to evaluate. I'm doing stoich problems from one reactant to another to figure out how much I need and figure out who's the excess and who's limiting the problem. Okay? So the first thing I'm going to do is I'm going to go into liters. You may say, why am I going into liters? Well, eventually I want to get into moles, and molarity is moles over liters. So let's go into 1,000 milliliters is 1 liter, and this gets me into liters. And now I'm going to use, and this is new, I'm going to use molarity. Okay, 2.73 moles of it is in 1 liter. So I'm going to use this right here as my gateway from volume of a solution, which is normally given, and its molarity to get moles. And now if I've got moles, I can put that into my mole ratio and do stoichiometry. So liters go, and this gives me moles of iron nitrate. Great. I want to get rid of iron nitrate. Okay, here comes the stoich part. We're going to use the mole ratios, NO3 to the 2, E to the iso. And then, of course, we're going to go to NH4, 2, CO3. And it's a 1-to-1. We did a lot of writing to cancel that out. You might say, well, I don't like doing that, but hey, it's a good practice to do that. So I've got moles of ammonia carbonate. Now, honestly, if you're stressed for time, okay, as most people are sometime these days, you can stop at moles and evaluate with moles. But we're going to go back right to milliliters to finish this off, since eventually I have a question for limiting reagent. I'm sorry, for excess chemical. So I'm going to continue on. So I got moles of this. I want to get rid of moles to get my volume. What's my gateway from moles to volume of volume? It's my molarity. And since I have ammonia carbonate, it's not canceled out. That's why it's good to use your units. There's 2.93 moles per 1 liter. Okay, and now I've got liters of the solution. I want to go back and evaluate to milliliters, so get rid of my liter. And of course, 1,000 milliliters. All right, so there's our Stoich problem using molarity, and of course these two spots here were my gateway from volume to moles, okay? And what I do is I multiply that through, and what I get is 116 or 116 point, I don't know, 468, we'll say, milliliters of what? Of ammonium carbonate. What does that mean? Okay, what does that mean? Well, that means given the exact amount of iron nitrate, to completely use it up, I need to have at least that amount of ammonium carbonate. Okay, and guess what? I only have 78 milliliters of ammonium carbonate. So I do not have enough ammonium carbonate to make all of my iron nitrate disappear. So this is my excess chemical. This is the chemical that is in larger quantities. Okay? So I found my excess, which means, okay, my limiting reagent, okay, is going to have to be my ammonia carbonate. But the question that I have below states how much excess chemical do you have? So I need to figure out exactly how much excess, or exactly how much iron nitrate is going to be needed to make, okay, to make all of the ammonia carbonate disappear. So that's our second Stoich problem. So the green's pretty annoying, so I'm going to go back to black. And here we're starting with 78 milliliters of ammonia carbonate. All right, and we're going to go to volume. So I'm getting rid of my milliliters, and I'm going to volume because I want to use the molarity. Okay, 1 liter, and for ammonia carbonate, the molarity is 2.93 moles per liter. And now I have moles of ammonia carbonate. I want to get rid of ammonia carbonate. Here's the Stoich part of the problem where we're getting rid of one chemical to get another. And we are answering about, or trying to find something about iron nitrate. And it's a 1-to-1. I know, cumbersome to do. But now we know the units left standing is moles of iron nitrate. Last thing we want to do is convert that moles into volume, and for iron nitrate that's 2.73 for 1 liter. Moles cancel, and I want to convert my liters into milliliters, and there's 1,000 milliliters in 1 liter. And what do I get? I get 83.714 milliliters of iron nitrate. What does that represent? That tells me exactly how much of the excess chemical I needed to make all of my ammonia carbonate disappear. If you check this out, 78 milliliters of ammonia carbonate, okay, for all of it to be to disappear and be the limiting reagent, I have to have enough iron nitrate. Well, we need exactly 85.7. Well, guess what? We have 125 milliliters. We have more than enough iron nitrate to make ammonia carbonate disappear. That's why this chemical is the excess. Okay, it's excess by how much? Okay, well, If you subtract 125 from 83.7, that's how we get the excess chemical. So let's do that. 125 minus 83.7, 4-ish. Okay, I'm just subtracting how much I have and how much of it is going to react. And I get something close to 41.3 milliliters of the iron carbonate. Okay, I'm sorry, of the iron nitrate. Who the limiting reagent is, of course, that's the ammonium carbonate. It's the chemical that runs out first. It limits the reaction because we have enough of it to make it totally disappear. Notice this didn't totally disappear, so what stopped or limited the reaction was this chemical, because we had more than enough to make it work. Okay, so last piece here is calculate the amount of moles of precipitate produced. So now I'm finally going to ask about the precipitate. So I want to know how many moles of precipitate do I need. So I'm going to answer about that question. Now the big mistake people make, as I've talked about, and again this is just something we're adding or we talked about already before, is that you can't start with the excess chemicals, start with the limiting reagent. However, you could start with what? You could start with exactly how much of the excess did react if you want to use iron nitrate. You can't start this Stoich problem to answer the grams of this precipitate by, okay, using the excess amount. All right, so if you want to start with iron nitrate, you can start with 83.7 grams of milliliters of iron nitrate and then do the Stoich problem to get to iron carbonate. Or you can take the safe bet, use the excess chemical, okay? You'll overestimate your answer if you started with the excess chemical. And we've covered that, and this is nothing new. So now we're going to get the amount of moles of precipitate. I didn't ask for grams. So I'm going to do my 78 milliliters. I'm going to keep the safe bet, use my limiting reagent, okay, of ammonia carbonate. Okay, I'm going to, guess what, convert to liters for obvious reasons now, okay? And I'm going to use the molarity, which for ammonium nitrate was 2.93. And for every 1 liter, there's 2.93 moles. Now I'm into moles. Hope you guys are into moles. Okay. And now I got moles of ammonia carbonate. I'm going to get rid of ammonia carbonate. CO3, 1 FeCO3. It's a 1-to-1. You got now moles of iron carbonate. And that's all I wanted. Okay, just moles. Kept it simple. And you get 0.22854, I think, moles. And of course, we started with 2 sig figs in our conversions, okay, or at least the limiting number of all of this, of all of our measured values, is 2 significant figures, so my end would have to have 2, so I'm going to round to 0.23 moles of my precipitate, which is iron carbonate. Not terrifically hard, but a lot of chemistry involved there. And hopefully you followed that all. And please go on to number 1. I have a key, of course, in the website. And that's your homework. Thank you and good day.